Okay, so I'd like to thank Molly, follow everybody in thanking Molly for bringing some of my favorite scientists to one place. And even though we knew we were talking one after the other, we didn't actually coordinate the slides. So as you will see in a moment, but you got a bigger introduction to this topic, so to the specific topic I'm going to talk about. Okay. As you all know, one of the original purposes of GWAS was to identify genes that are important for traits, and in order, for example, to learn about disease etiology and to identify drug targets and so on. And then here, this may be a, okay. So this may be a familiar figure. So it came a bit as a surprise that GWAS signals were distributed very widely in the genome. And as Jonathan pointed out, this is the Manhattan plot for schizophrenia. And you know, one gene does stand out, as happens occasionally for other traits. So this is this locus in the HLA region that Jonathan just mentioned, that's dotting my eye over there, but it's on a highly polygenic background. And so here's another way to look at this data, which might seem a bit familiar. Which is this graph that Jonathan described from the work of Pasaniuk and colleagues, where essentially what we're seeing here is that the amount of heritability on a chromosome is proportional to its length, where, you know, occasionally you have things stick out when you have major loci, as Jonathan showed in more examples. And as Jonathan presented, then this picture occurs in several kinds of analyses, and for many traits, there's variation in degree, as you saw. So so if we return to this purpose of finding important genes for traits, then we could interpret these findings in two ways, simplistically. One is we could say, okay, maybe the bulk of genes are important for many traits, and an alternative that I'd like to explore today is that maybe there's some other factors that affect heritability other than importance that factor into the heritability, and therefore the results of GWAS are not as straightforward as may seem, as you may think. And I'm going to take like a slightly different tack at it than what Jonathan presented. But first, let me be concrete about what I mean by an important gene. And to that end, I'm going to just use a tweak of the model that Jonathan presented, their omnigenic model, where, so you know, if we think that most heritable variation in traits comes from variants that affect gene expression, and now let's simplify things and assume we're looking at a single tissue, and that the trait value is determined by the expression level of genes in that tissue. So each gene expression level has some effect on the trait. And now let's assume that we have a SNP that affects the expression level of gene I in cis. That SNP would also affect could affect the expression level of other traits in trans, for example, because a gene could be a transcription factor, or more generally, it could be a protein that modifies the activity of other genes. And now if we want to calculate, you know, the effect size of the SNP on the trait we're looking at, then, which is denoted by A over there, then you could think about it as a product of the effect of that SNP in cis on the expression of gene I, which I denote by alpha here, times the effect of changing, the effect of the change in expression it induces in gene I on the trait, where these effects include both the direct effects of that gene in cis and also the indirect effects. So my definition for this talk of importance is just going to be this gamma square So just to emphasize, because you just saw a small, this is a tweak on a model you just saw, then what I'll define as importance could be, a gene could be important either because it has a large direct effect on the trait, so that's what Jonathan defined as a core gene in the context of the omnigenic model, or it could be important because it has a large effect in trans, mediated through the expression of other genes. So the example would be a transcription factor. So now we define the importance of the gene. So how do we expect importance to factor in to the signal that we see in GWAS? So in GWAS, as you know, what we do is we regress the trait value against the genotypes at each SNP. And from that regression, we obtain a significance level for the association. So what actually determines this significance level? So let's assume for simplicity that our SNP is a causal one to set aside the problems that have to do with LD. So generally what we'd expect is that if that SNP has a larger effect on the trait, then it's going to be easier to establish an association. But the minor allele frequency also matters, because if the frequency of the allele is very low, then we'll have very few of that allele in our sample, and it would be harder to establish that the SNP is associated with a trait. And the way that the two of these, the effect size and the minor allele frequency, combine is through the heritable variance that you see over here, which is to a good approximation directly maps to the significant level. Okay, so now where does the importance fit into this picture? So the effect size of the SNP is where the importance comes in, where per the model, the simple model I showed you, the effect size is just the product of the effect of that SNP in cis times the importance of that gene. However, we also have the minor allele frequency coming in, and what affects that? So selection on our trait would affect that, because our SNP affects the trait value. If our SNPs affects other traits, then selection on other traits would also affect the minor allele frequency. And in addition, demographic processes, notably changes in population size, would also affect the allele frequency. So now if we want to, we could use population genetic models in order to understand how these factors combine to determine heritability, and from that, perhaps that's going to teach us something about how to interpret these GWAS signals. So let's first consider a model where the only trait under selection is the trait we're looking at. And most complex traits are thought to be under stabilizing selection, which means that the trait value has some optimum, as you see over here, and as you move away from that optimum, then the fitness goes down. So let's assume that our trait is under stabilizing selection. And this model of stabilizing selection has been solved by many, going back to Sulliwright. And the first part of this solution is to realize that the selection acts against. So if we're looking at the SNP that affects the trait, selection acts against the minor allele, and the selection coefficient for the minor allele scales like its effect size on the trait squared. So in terms of our model for gene importance, the selection coefficient is just going to scale like the effect of that SNP in cis times the importance of the gene. And we're going to use the scaled selection coefficient just to account for the effects of genetic drift. And the important thing is that that too scales like the importance of a gene. So now, in order to look how in this model, what kind of heritability we're going to get, then I'm going to first make the simplifying assumption that all mutations affecting the expression of a gene in cis have the same effect size, and later I'll relax that assumption. So in this case, the contribution of a gene to heritability has also been solved. And what you see it is over here. So this contribution is on the x-axis, where on the y-axis we have our measure of gene importance, which is measured in these units of the scaled selection coefficient on cis variants. And what you see is that when selection is weak, so when the scaled selection coefficient is well below 1, then it doesn't affect allele frequencies, and therefore the contribution to heritability scales like the effect size square. So we have like this linear dependence. But then when selection becomes efficient, relatively roughly around a scaled selection coefficient of 3, then its effect on the minor allele frequency actually cancels out with the importance to produce an approximately constant contribution to heritable variance. So now we could introduce a variation in cis effects, which we do here in a certain way, and that modifies the shape of the curves, but it does not affect the qualitative behavior that when selection on cis variation is effective, then you get this plateau. So what we're essentially seeing here is, at least per this simple model, is that once selection is efficient, then the gene's contribution to heritability is insensitive to its importance. In other words, if we're looking at cis variation to an important and an unimportant gene, they're going to contribute the same. We're going to see the same GWAS signals. Okay? However, this model is quite naive, because we know that a genetic variation that affects one trait affects many other traits. So in order to consider the effects of this pervasive pleiotropy, next we could consider a model where we have multiple traits under stabilizing selection. So our focal trait would be the first trait, and then we have many other traits. And we're assuming that fitness is maximized at some n-dimensional phenotype, and as you move away from it, fitness goes down. So this model has been solved as well, and as before, selection acts against the minor allele at the SNP affecting our trait. But in this case, the selection on the minor allele is actually proportional to the sum of effect size squared over all the traits that are under selection. So in terms of our model for importance, the selection coefficient is going to be the effect of the SNP in cis times the number of traits under selection times the average importance of this gene over all the traits that are selected. Now, in this case, I'm going to assume that selection on cis variation is effective, so we're in this strong range. And in order to study how the importance affects the contribution to heritability, then let's make some more assumptions. Let's assume that traits generally have few important genes and many unimportant genes. And we're going to focus on a gene that's important for our trait, and assume that it's important for a proportion P of traits in general. So in this case, the average importance of our gene across traits is going to be linear in this proportion of traits P, and the selective constraint acting on cis variation in this gene is also going to be proportional to this average importance, or to the proportion of traits that this gene is important to. So here you see the contribution to heritability of our important gene, where on the x-axis we vary the degree of selective constraint on cis variation, or equivalently, when we're on the left end of this curve, then our gene is important for our trait, but for few other traits, and therefore cis variation is not under that strong under that strong selection constraint. And what we see is at this end, when selective constraint is weak, then the contribution to heritability is actually going to scale with the effects with the importance of that gene to our trait, okay, which is one end. On the other end, when we have when cis variation is under strong selection constraint because it's affecting all our traits, then in that case, what's going to happen is that actually an important and an unimportant gene are going to contribute the same to heritability. Okay, so again, we have this, at this end, the contribution to heritability is insensitive to the importance of the gene to our trait. So in reality, you might think that, genes should vary in their degree. Genes that are important for our trait could vary in their degree of selective constraints or in the number of other traits that they affect. So we could have genes that are important for our trait, that are specifically important for our trait and for few other traits, and we could have, on the other end, genes that are important for our trait and for many others, such as transcription factors, for example. And one of the interesting implications of this is when you do a functional enrichment in GWAS and you're looking at different sets of genes that perform different functions in order to learn on what kind of genes are important for the trait we're looking at, then in fact you're not only comparing the importance of these different functional annotations, but you're comparing a measure that combines the importance of these genes to our trait, but also their degree of selective constraint, which may vary. What I left out today is also that, the effects of selective constraint that you see here are actually accentuated in large GWAS that are based on genotyping common variants. So in that case, the curve you see here would go down sooner. Also, demographic history, such as changes in population size, have substantial and non-trivial effects on this relationship between importance and heritability that we see in GWAS. So, in closing, I'd just like to recap the main argument here, which is that in GWAS, the thing we're measuring is the distribution of heritability in a trait across the genome. And that distribution reflects numerous mutational perturbations to the phenotype, and these perturbations are typically too small for us to measure in any experimental assay. So I think it's clear that GWAS are telling us, giving us a very unique insight into biological function. The important point, though, is that the relationship between our signals in GWAS, or heritability, and function is not a straightforward one, because these mutations that we're seeing in GWAS have sifted through the sieve of evolution. In particular, the relationship between their effect size and frequency, which together make up the heritability and determine what we see in GWAS, are strongly affected by selection and demographic processes. And I guess the main point is that it's essential, in order to interpret the signals from GWAS, to account for how these processes of selection and demography affect these signals. So I'll just close by first thanking my wonderful partners in this work. So there's Yuval over there, and Nasa, and Jonathan, and mentioned that, like other people here, we're also looking, or I'm also looking for students. So if you're interested or know somebody that is, please let me know. And yeah, I'll finish with that.